warmly welcome everyone to today's workshop. Thank you so much for joining us. My name is Johanna Siljakus. I'm a consultant with ADB's Transport Sector Office, and I will be moderating today's session. And yes, so I'd like to extend a really big welcome to you to this online training workshop on light electric vessels with a focus on the Pacific region. And if I can have the next slide, please. Thank you. So today's workshop is co-organized with GIZ and the University of Applied Sciences Emden Leer from Germany. During this session, you'll be gaining insights into business potential, technical feasibility of electric light vessels for the Pacific Island countries. And also, among others, learn about the GIZ-led low carbon sea transport pilot project in the Marshall Islands as an example. The session has been catered for Pacific Island audiences in particular. However, everyone from other regions in Asia and beyond is very welcome to join us and learn about this very interesting topic. So the workshop is arranged under the umbrella of the e-mobility support and investment platform for Asia and the Pacific. This is a knowledge platform that aims to build capacities and support the scale-up of e-mobility in the region. It's led by the ADB, Asian Development Bank, and it forms part of a global initiative supported by the GEF, the Global Environment Facility, and UNEP as part of the Global Electric Mobility Program. We also have other supporting partners, including the Green Climate Fund, the Republic of Korea, E-Asia Knowledge Partnership Fund, and Japan's High Level Technology Fund. And if I can have the next slide, please. So before moving ahead with introducing our trainers for today or kicking off the workshop itself, a couple of words on ADB's side and on behalf of the e-mobility platform. So first, we'd like to let you know that the support and investment platform for Asia and the Pacific now also has a website. So it's up and running. You can access it through e-mobilityplatform.asia, which is the address you can see on the screen there, or through the QR code on the screen as well. The website includes our upcoming events and activities, news, also webinar recordings, newsletters, blogs, and other kinds of knowledge products. If you wish to collaborate through, for example, writing a blog post with us, please get in touch. We're happy to discuss this further. And next, we have some introductory remarks on behalf of ADB. These are provided by my colleague Bert Fabian. He's Senior Transport Specialist at the Asian Development Bank's Emerging Areas Transport Sector Office. So let me hand over to Bert for his remarks.
Thank you very much,
Thank
Johanna.
you.
Really, I wanted to take this opportunity to thank the GIZ and also our colleagues from the university for sharing their experience in this quite an important topic, future of electric vessels, electric inland water transport. The reason also what I wanted to provide some context, majority of the inland water transport vessels and also coastal water transport are using diesel engines. And in many cases, these are second-hand diesel engines using relatively low quality fuel and hence emitting high levels of air pollution in addition to greenhouse gases. So it impacts the health of such coastal cities or especially in areas with big rivers. When I was in Bangkok, the um, water transport in the canals, which carry a lot of people, very useful, was emitting quite uh, like smoke, like a black smoke that you can see. And again, this influenced by the second-hand engines. And similarly for the big river in Chao Phraya, there's also such emissions. Now, looking at the overall contribution to air pollution in Bangkok, it may be small, but because there are fewer number of such vehicles, but they contribute large emissions compared to their numbers. Anyway, the point is we also see the electric water transport as a vehicle that not only will contribute to reducing greenhouse gases, but also improving the overall quality of life and better air quality in coastal cities, in particular, but also in riverine cities. So there are a lot of questions. I think it is not clear how this electric mobility can play a role, and we would really love to hear more from our colleagues from GIZ and university. Thank you very much. Back to you, Anna.
Thank you so much, Bert. Um, Let me move forward with some house rules for this session before kicking it off officially. So your mics, all of your mics are muted. So please keep those muted as well, unless you're invited to speak. We will have, I think, around 3 Q&A sessions during today's session. So after each of the speakers, there will be space and questions in those sessions. And at that time, you can raise your hand and we'll enable your mics for you to ask your question. But you can also ask questions through the chat, the comments box or the chat box. So please, and those questions can be shared throughout the session. We'll gather them to the Q&As and ensure that they will get asked during the Q&A session. So please feel free to add any comments, any questions you have in the chat. And as said, you can also, during the Q&A sessions, you are also allowed to, I think you should be able to kind of signal with your hand that you wish to speak. We will be recording this session. We'll be uploading the recording online. You will actually also receive the PowerPoint slides from today per email latest next week. And yeah, let's move forward then to introducing our excellent speakers for today. So as mentioned earlier, today's workshop is arranged in collaboration with GIZ and the University of Applied Sciences Emden Leer from Germany. And we are really fortunate to have 3 highly knowledgeable trainers running today's workshop. So let me introduce them in the order of the order that they will be speaking today. So first we have Raphael Held. He's the project director of the Low Carbon Sea Transport Project at GIZ in the Marshall Islands. He has over 7 years of experience at GIZ and a strong background in marine operational engineering. He's led the piloting of practical solutions such as hybrid propulsion systems, electric cargo boats, and climate resilient vessel designs, combining cutting-edge technology with deep community engagement. Then our next speaker will be Henrik Richter Alten. He's a naval architect from Germany, currently associated with the University of Applied Sciences, Emden, Leer, and the Fraunhofer Institute for Wind Energy and Energy System Technology. He specializes in low carbon maritime transport with a focus on wind and solar electric propulsion systems and works as an international consultant focusing on the implementation of technology that fits people and place. And he's worked with electric vessels both in the Marshall Islands and in Uganda, among other places. And last but not least, our third speaker is Jonas Schwartz. He's a research associate at the University of Applied Sciences, Emden Leer as well. He's specializing in mechanical engineering and sustainable design and has over 15 years of experience teaching mechanical engineering students on topics relating to low emission maritime technologies. Among others, he's training students practical skills on board of a solar electric research vessel. And his strengths lie in hands-on engineering, education, project-based learning, and developing real-world solutions for sustainable mobility. So we're very happy to have all of you here. Very excited to hear about your experiences with electric vessels. So let me now hand over to you. So we will be starting with Raphael's introduction and presentation. So I'll hand over to you, Raphael. Thank you. The floor is yours.
Thank you very much. Johanna, let me just share my screen. If you can tell me if you can see the presentation now, that would be great. Can you see the screen?
Not yet. It might be loading.
Okay.
Yes, now it's
I think you
loading.
should see it now.
Yes,
Okay.
there's the box on top. Yes, but now we can see it fully.
Perfect.
Thank
Thank
you.
you very much, Johanna, for the facilitation and moderation of this session today. My name is Raphael from the German International Corporation, as you have said, and I'm very grateful that you have reached out to us in order to provide some insights from this pilot project that we've been undertaking now in the Republic of the Marshall Islands in Micronesia since 2017. I will give you, in the first place, I will give you an overview about the general background of this project and then the specific components. And as well, I will try to bridge the gap to the topic why we come together today, electric mobility and electric propulsion. So let me start with sharing some background information. This project was commissioned by the German Ministry for Environment in the year 2017. The overall budget of this project is until today nearly 20 million US dollar. And we've been working since 2017 with our political partner in the Marshall Islands, the Ministry of Transport, Communication and Information Technologies. Next to the ministry, there was an entire set of different partners nationally in the Marshall Islands, but as well regionally and internationally. You can see some of them listed here as well. The colleagues from the university, Emden, Leer, in this case, I think Hendrik and Jonas, who will also provide some insights after myself, have been working for this project also already over the last few years. The project is split in total in 3 different components. We have the component that is working on the transportation within the vast atolls of the Marshall Islands. The second component, the so-called inter-atoll component, has been trying to develop concepts for shipping between the atolls of the Marshall Islands or international shipping. You can see it here reflected in the center. And as well, the project has been providing capacity building measures for delegations of the government of the Marshall Islands to take part at negotiations at the IMO level, at the International Maritime Organization. I have a little technical problem here. I just mentioned it. The slides are moving automatically. I never had this before. I tried to avoid it. Just if you're not surprised why I'm just keep turning the slides, it's the computer. So the background of this project is the NDC commitment of the Marshall Islands. The Marshall Islands have been the first Pacific Island country in 2015 in the COP in Paris that committed to a decarbonization in the domestic shipping sector based on those discussions in Paris between the former late Minister for Foreign Affairs, late Tony de Broom, and the former Minister for Environment, Dr. Barbara Hendricks from the Ministry for Environment. In 2015, this project was endorsed and commissioned 2 years later. Now, earlier this year, in February 25, the NDCs have been revised, and basically this is the background of this project. The background is to provide technology and insights to allow on an exemplary level the Marshall Island shipping operators to reduce carbon emissions in the domestic shipping sector. So as I said, the first component, the inside lagoon component, that was one of the components that started first in the project around about 2019. Hendrik was one of the consultants as a boat designer, naval architect, to design new concepts, new boat designs that can be built locally, operated locally by Marshallese people, and as well maintained locally. This project component is closed from our perspective at the moment, but the National Energy Office has continued to financially support the NGO One Island in Marshall, which means the Canos of the Marshall Islands, for medium term to continue building and deploying those boats. You can see here on this slide at the moment, even already one of those hybrid designs we came up with as a prototype in 2020, 2021, where to the warm catamaran, which you'll see more precisely on the next slide, a small solar panel was mounted together with an electric outboard engine to already show what could be possible with very small, minor effort built by the people there in the Marshall Islands. Here you see the two different designs, the outcome of those boat building programs we've been facilitating. The left design, the catamaran, on the right side, the Harry Broer, both designs influenced by two different naval architects and now deployed and used in the neighboring islands of the Marshall Islands. By neighboring islands, I mean the outer islands, the more remote islands, because I myself am based in Metro in the capital island. I'm really sorry that the slides keep moving here. This is not really what I foresaw, but I tried to keep track. And at the end of the day, this component was concluded last year with the publication of two construction manuals for each of those designs. They are publicly available online. The link is shared in this presentation, and you can just download those manuals. And if you wish, you can even build yourself such a boat. We are very happy of this outcome. The knowledge shall be shared more into the Micronesian region soon, and actually the project is continued. I will share a few words about this later. Coming to the
Raphael, sorry to cut you. Would you like
Yeah.
me to share your presentation instead?
Yeah, you can do that. Yeah. Slide number 10 now. Sorry.
Oh, sure. All right, one moment.
Thank you. That's great. That's
Sure.
going to be more comfortable, especially now.
All right.
More the focus will be on this component. This component is not yet concluded. What you see here on the first slide to the inter-atoll component is basically what we want to, or what we did introduce for the Marshall Islands over the last few years. So the background here is the Marshall Islands, consisting of about 29 atolls on a very large sea surface area, need and depend on the regular services of ships this size. This size is about 500 gross tons. Those ships are operated by the government of the Marshall Islands, the state-owned enterprise Marshall Island Shipping Corporation. And the Marshall Island Shipping Corporation, short MIC, MIC is by legal act meant to provide shipping services to the outer islands on a regular basis. And we've been trying to come up with a concept ship that would operate on a much lower fuel consumption. What you see on the right top side is the sailing vessel Kwai. Some of you might be familiar with. The Kwai was operated between Hawaii, the Line Islands in Kiribati, and the Cook Islands over nearly 2 decades, until the Kwai was purchased by the Marshallese government at the beginning of the pandemic 2020. And the Kwai served as a model and as a research ground, basically, to develop the Churenai, which you see on the right bottom. The Churenai is, we can go to the next slide, please.
I couldn't go over to the next slide. Just a second.
Okay, well, thank you, Christina. We see here the technical specifics of the ship, and I think I mentioned a few already. The ship was built based on a very comprehensive needs assessment in the islands, which we undertook at the beginning of the project. This is the outcome. Eventually, the ship was built in South Korea with a total budget of about 4.4 million euro, which equals about 4.8 million US dollar at the time I made this presentation. Next slide, please. There's some more specifics about the vessel. At the end of the day, the ship does fulfill all those very special island requirements we analyzed over the years and is now operating in a regular domestic service. I want to highlight here just briefly that the ship is internationally registered with the international flag of the Marshall Islands, and the ship is also built under Ajax class, under the Korean register. And we are still working on the certain elements of the ship, in particular the sailing rig, the Indo sail rig that was developed in a very close partnership with the university Emden Leer and other external partners, including the shipyard, of course, in South Korea. Next slide, please. Just to give you an idea how long this took, as I said, we started in 2017 after a very comprehensive baseline assessment. A catalog of options was developed, and eventually the Marshallese government and all those project stakeholders agreed to build a new ship, to design a new ship, because the alternative has been at that time to modify an existing vessel, but we found this joint decision to go for a new design, and this design process took over the year 2019, 2020, until we could start the tender in 2021. Next slide, please. So from the tender, the bidding process, it took another year until the contract got negotiated and the construction started eventually in 2023. Last year, the ship was finalized in June. We sailed the Churanai over to the Marshall Islands in July, and now she is operating in the Marshall Islands. We can continue. As you see, the ship was very much received with a very high interest from the government. In the meantime, I see that neighboring countries are very much interested too in this type of technology. I want to elaborate a bit more in detail, particularly about the electrical propulsion. We can continue, please. One aspect of our work is training. There was a training center established. We're currently developing further courses, also with a focus on electrical propulsion. That's something I'm sure Henrik will mention a bit later more in detail. The training is absolutely essential. Until now, seafarers in the Marshall Islands haven't really achieved a lot of capacity building before, and now this is more regulated. It's hosted by the College of the Marshall Islands, by the National College, basically, and the first graduates are already working in the shipping sector now in the islands. We can continue. One major policy document that got established and endorsed 2 years ago by the Marshallese government is the roadmap. The roadmap for sustainable domestic maritime transport. This roadmap paves the way for full decarbonization until the year 2050, and is also available if you would want to have a look how the Marshall Islands developed such a document and how they go about the implementation of the different activities resulting in the final goal to decarbonize the domestic shipping sector in the Marshall Islands. We can continue. And this will bring us to the last section. I will try to give you a few more details about the electrical components in the new ship. I will start here with the parallel hybrid transmission, PHT. PHT was a system we purchased in discussion with the Korean shipbuilder in Belgium, with the Belgian company Esco Power, and Esco Power installed this system, and we're now testing it. There's still room for minor improvements. I can also elaborate on a bit later, but generally what we achieve by this system is basically a higher rate of redundancy in the ship system itself. And of course, we can reduce the fuel consumption and be much more flexible if the ship is sailing. It even allows us, if the ship is sailing in fair conditions, to generate up to 45 kilowatt of electrical power that can be stored in a battery system or feed into the hotel load of the vessel, and basically allows for zero emission ship operation in certain conditions. As well, the ship is equipped with an 11 kilowatt PV panel system that is retractable, foldable. You can see it on the right bottom side. Now it's basically not in full operation, but when the ship is sailing, those panels on the side you can see on the stern, on the starboard side, would be put up with hinges and then can increase the surface area. We can continue, Christina. So as I said, this system allows for higher redundancy as well flexibility. We see five operating modes to propel the ship. For example, as I said, we can just use the main engine, a diesel combustion engine, together with the power takeoff mode. We can only use the power takeoff mode when the ship is sailing, as I said before. We can use the propeller in the milling recuperation mode. And as well, we intend to use the power take-in mode, which is not fully functional yet, but this is something we want to continue to develop with the children. That's our mission. Now we have 2 years left. And of course, the goal is to have the best design for the second order. I can say that the neighboring country in FSM is very much interested to have a similar ship, and then those lessons learned will feed into a revised design. We can continue, Christina. Here's a more closer look of the electrical system on board for those who can follow. I will just briefly summarize it, that we can see here the main engine with the PHT system and the PTO, PTI driven E-machine. On the right side, we see those PV panels feeding onto the main bus bar, and we have two auxiliary engines, two generators, each up to 45 kW, that allows for a really safe, reliable, and flexible low carbon system, I would call it. We can continue. And I think that's another background information. We're talking about e-mobility. The Marshall Islands, since 2018, have the electricity roadmap in place. And I would rather consider our maritime roadmap as an add-on. We can continue to the next slide. That's what I already mentioned. And both framework documents are guiding the way for the work that is done in the Marshall Islands. In particular, of course, we're working on the maritime sector, and I'm going to show you just a few more slides before I conclude, because we have 20 minutes. Christina, the next one is something we see in the roadmap, is the recommendation for using electric outboard technologies, for example, on those lagoon boats. You see it on the right top. That's the one I showed earlier. If we continue to the next slide, you can see a few more details. This is what I already mentioned. Sorry, I thought it's already coming. That's the inter-atoll shipping with hybrid solutions. Of course, the infrastructure needs to be improved in the Marshall Islands. That's something that is ongoing. I can literally see it being there now for nearly a decade. I can see that the amount of PV panels in the city of Metro is increasing drastically, and the entire power grid in the urban area is improved over the years. And I do see strong improvements in that sense. The next one, please. Yeah, I think I would leave it to that with my overall insight, talking about the pilot project that is implemented by GIZ and many other partners in the region and globally. We are very happy about the outcome. I can say from my perspective, this is a good start. We've been working there now for 8 years. I think it is only a start. So I think I'm convinced that we have to continue in all those different areas. And I'm very much excited as well to see now the presentation from Henrik and Jonas, because the interest is there. The people in the islands, they really want to go down this way and use fossil fuel free transportation means, especially in the maritime sector, being so dependent on maritime transport in the islands. I think in the Marshall Islands, we've been lucky to have such strong and interested, innovative partners. I hope we can extend and share this knowledge in the upcoming years also more in the larger region, but also beyond the Pacific Island region. Thank you very much for your interest and attention. And if you have any questions, I'm happy to answer them. I'm concluding now at 20 minutes because those details I've basically shared. Thank you very much.
Thank you so much, Raphael. This was really fascinating. And it's actually interesting to hear. We just yesterday had a training workshop on e-mobility roadmaps, and it's interesting to see how the roadmap in Marshall Islands has been integrated also with the maritime or water-based transport roadmap. So that's really fascinating. Are there any questions at this stage to Raphael? I have not received any to the chat so far, but this is your chance to ask any question from Raphael at this stage. Please do share your questions in the chat. Maybe I was actually curious if you could talk a little bit about the economic feasibility of the Jura ship. Is that
Yeah.
how did that work out?
The economic feasibility, I think that's something we're still looking into. But as of now, I can say the ship in average operation consumes about 80% less fuel. Let's take an example of a conventional Marshallese government ship. Would look nearly the same from the outside as the Churanai, just without a sailing rig, obviously. Would need about, with the current fuel prices, about 4,000 US dollar of diesel oil per day on a 24-hour open sea voyage between the islands, whilst for the Churanai, we arriving at about 400, 500 US dollar per day. So there's quite some saving potential that makes it so interesting for the operator, and even brings the operator, the government, into the position to say, okay, we rather take the Churanai to go on those trips because we constantly facing budget constraints and similar. I am just working on something like a comparison of how to ship goods from Metro to Pohnpei. Pohnpei is one of the 4 states in the Federated States of Micronesia. Pohnpei wants to ship copra cake from Metro to Pohnpei. Metro wants to sell that copra cake. So we're thinking about sending the Churanai with 200 metric tons of this cargo to Pohnpei in November. And we estimating about 220 US dollar per ton of cargo, whilst the container shipment is about 320 and the Marshallese conventional government ship will be about 450. So I think there is quite some saving potential in an economic sense, in a monetary sense, next to all the other maybe soft benefits we see. We see a complete movement in the Marshall Islands where a young generation sees that change can be done by themselves and taking over responsibility by signing up in the training center and coming back to their ancestral roots. The Marshallese people, I think I can say, are very proud navigators since hundreds of years. And I think by introducing those smaller boats where Henrik was involved, as well the big ship, I think that's something that is also a benefit you can't put in numbers as easily.
Yeah, no, that's really interesting. Thanks, and thanks also for bringing up those soft benefits because it obviously goes beyond the economics here.
Mhm.
Um, I see no further questions, so I wonder. I mean, feel free to send your questions through to Raphael, also for the consequent or the Q&A sessions that we'll have afterwards. But maybe we'll then move forward to Henrik's presentation at this stage, since I don't see any further questions. And as said, please post your questions in the chat at any time. So thank you so much, Raphael. I think this was extremely informative. So thanks again. And over to you, Henrik.
Yeah, thank you, Johanna. Let me quickly pull up my presentation. Here we go. Should pop up now. Can you see it properly, or are
Yes.
there any black windows in front of it? No.
No
Great.
black windows. We can see it.
No black
Well,
windows.
thank you.
Awesome. And I also have my cursor. That's perfect. Just as tested. Yeah, so since we now got the wider overview of our project, or of the project in the Marshall Islands and the associated project components from Raphael, I will now go with you a little bit deeper into the technological part of electric propulsion on the water. So what I first wanted to do is a little bit of expectation management here, because as you will see, replacing existing combustion-powered boats with electric solution and expecting that they can do the same, exactly the same thing is possible, but you will see that that has some consequences, and that must be clear from the beginning, especially when you're looking to implement project about these technologies. That must be clear from the beginning, that there are no unrealistic expectations, because that is something that very often I come about, that people just think, okay, we just swap the engine, combustion to electric, and then problem solved. It's not that simple. I mean, it is simple, but not that simple. Also want to talk a little bit about solar electric propulsion, actually mainly about solar electric propulsion. Have a detailed look with you on the individual components of such a system. So we're really going into the hardware. Also have a look at the challenges for sustainable implementation, in particular in the Pacific region. Although I have to say, Pacific region, especially if you also look, count in Asia, Southeast Asia, that is very, very different. So you find very, very diverse conditions there. So it's a bit difficult to cover that in such a short time. But I think I can give you some pointers of what to pay attention on, and that can already be helpful. Then we'll also look at an exemplary case, business case. Raphael mentioned in one of his last slides as a recommendation to establish a ferry service within the Majuro Lagoon. And we will look exactly at this business case, where we today have a combustion-powered boat, and where in the future we might see an electric or solar electric boat operating. Yeah, and after that, Jonas will take over and give us a little bit more insights into a case study that we've conducted at the university in 2016. I mean, it's still ongoing, but it was started in 2016 with a bit different, different starting point. As I mentioned, it's hard to replace one-on-one without changing your expectations, and this is what has been done here. So this was the goal was to replace one-on-one, and you can really clearly see how that affects the system and what kind of consequences that has. All right. First of all, the ideal use case. So to get you a bit more excited about it, what you can actually achieve with this type of technology is a vessel that produces its own fuel, takes you around at a good speed, at your schedule without need to wait for conditions like wind when you're sailing, and you never have to put any gas in, and it's essentially moving you around for free. And that's not a dream. That's actually what you can get when you implement such a boat. On the photo here, you see the largest solar ferry of Africa, at least the largest one I know of, which we launched earlier this year on a small lake in Uganda. And it can exactly do that. You have unlimited range as long as there is daylight. So even when there is complete overcast by the clouds, you can still achieve cruising speed without touching your battery charge. So this really gives you virtually unlimited range in that condition, and even beyond. So far, I think we never had to charge from the public grid. So this ferry is completely independent as of now from any outside energy sources. Okay, expectations, as I introduced. With the electric propulsion, you have basically the same constraints as we see in the automotive sector. The energy density in the batteries is a lot smaller than you would have in the same volume of gasoline. That must be clear. It's way lower. So you have to be conservative with your energy. And what that means is cranking up the engine to high speeds, to big power I mean, you can do it, but it's really cutting short your range. And what that means is if you want to keep your system small and affordable, you should better look for protected waters, coastal waters, canals. We heard about, I think Bert mentioned canals in Southeast Asia in the beginning. Perfect application. Canals are great for these kind of vessels. You also want to look at the distances you go. You might not want to cover super long distances because then you somehow need a lot of energy and big energy storage, and that's expensive. And you also want to look at your speeds because, as we will see, the energy consumption increases exponentially with speed. And what I mean with exponentially is, to give you an example, with this vessel you see on the right, you can conveniently cruise at around 9 kilometers an hour with just consuming 2,000 watts. And when you double the power input to 4,000 watts, you're just doing 10 kilometers an hour. So you double the power, but you're not even close to double the speed. And that it doesn't make sense at all to go full speed. The boat's not getting much faster, but you just blow out all your energy. So, but in the trade-off, what this electric propulsion offers is a reliable service. You quite often on the output engines that are in use, you see that they fail in the worst situation. Sometimes particularly on the Marshall Islands, fuel is not available, so they cannot be used at all. They are silent. There's no toxic smoke or oil leaking into the water, which is a big plus for sensitive areas like coral reefs or pristine lakes like we see here on the right. So there is a lot to win here actually. And but as always, it's a trade-off. But to manage the expectations, it must be clear. You can replace one-to-one, but it's going to be really expensive. Quick slide about electric versus solar electric. In the following presentation, I will only talk about solar electric. The main reason is when you only have an electric boat, so that means there's an electric engine and a battery as an energy storage, you entirely rely on shore charging. The vessel cannot produce its own energy. That means while you're sailing, you're also not charging your battery with the solar power. So you need bigger batteries and you need a reliable public grid connection to charge, or you need to set up your own charging station on the shore with some sort of renewable energy source. And that's where the problem starts, because then you get involved in land. and real estate issues. So in the Marshall Islands, it's really strict, and I think in other places in the Pacific Islands as well, you have always land right issues, and it's really, really hard to access land for these kind of projects. So it just makes everything way more complicated. It might be different in other parts of Asia. Still, you would need land, and land is always expensive and difficult and hard to come by. So why not having the energy production on the boat itself, with the additional benefit that it can also charge while you're sailing? And theoretically, depending on the system setup, in some conditions can give you unlimited range. So actually you're charging more than you're consuming while sailing. Of course, it depends on the amount of solar panels you put on top. So, but that's why we mainly look into the solar electric propulsion. Basically, what that means is you can have a smaller battery because you have the charging option while you go. And smaller battery means it's less expensive, and it's also more sustainable because a battery is always a bottleneck when it comes to sustainability of electric propulsion. Also, in the following slides, I'll be talking about light solar electric craft. Jonas will later also talk about heavy solar electric craft. What do I mean with that is we're limiting the system voltage to 48 volts here. That is often done because 48 volts DC is considered safe. You can touch it, you're not going to get a stroke. It's easy to handle also for amateurs. It's usually easier on the regulation side, and just in general safe to work with, and kind of the standard for this size of vessel. Length can be up to 15 meter, displacement up to 15 tons, but then we're already on the pretty heavy side, and propulsion power up to 20 kilowatts. When you go much beyond that with 48 volt systems, you will either end up with a lot of engines or with very, very thick cables, because somehow the power, the amps, has to go through the cable, and then you need a lot of copper. So it doesn't really make sense to go beyond that. Also, you will have a hard time finding engines. Okay, let's have a look at the basic components. What you see in the background is a project that we've been working on for, it's a design study for UNDP. It's now going to be built in kind of similar to this one, a bit different, in New Zealand for island supply in Samoa. Maybe let's start at the engine. Of course, there's an electric engine. In this case, it's an outboard engine that you can just buy readily available. It has the same connectors and same mounting system as a regular outboard engine. Looks basically like the same. Only difference is doesn't need fuel, and you have to plug it into a power source. Usually in these kind of vessels, there is always some sort of battery storage as a buffer, because the solar power is not always reliable. So when you have clouds, or when you have different orientation of your panels, or when you want to go at night or late at the day, you have very big fluctuations in your output. So you need this battery to have a constant power supply for the engine. Theoretically, that would also work without one. But then we are really talking about extreme examples. Actually, I've seen some boats, very, very low budget boats, which just connected the solar panels to the engine. It's possible, but yeah, not really recommended. Battery size, of course, is always a discussion and needs to be carefully designed for the intended application. Yeah, further along the road, you have the MPBTs. We'll have a look at that in detail. Basically, that are just the solar chargers. So you can not hook up the panels directly to the battery. It's not going to work. It's going to damage your batteries. So you need something in between. And what we usually use are MPBTs. There are other technologies, but MPBTs is pretty much the gold standard. Yeah, and these MPBTs are directly connected to the solar panels. So essentially, solar panels feed into the MPBTs, MPBTs charging the batteries, batteries are supplying the engine, as simple as that. Oh, and then there is, of course, some sort of engine control, like a gas, like a throttle for controlling the engine. And depending on your setup, either a steering wheel or a tiller. Usually then the helm, like the throttle would be integrated in the tiller. But there are also different configurations available. And of course, what you need is a hull, or in this case, this is a catamaran platform. We're seeing it from the side, so you cannot see the other hull. Catamaran means it has two hulls. We'll also look at that later in detail, why that's beneficial for this sort of application. But in the first, at the first look, you can also use existing boats. Retrofits are possible, but there's definitely a benefit of designing vessels, also the hulls and the structure for solar electric propulsion. So there is a lot of potential if you design it to be used for this sort of propulsion technology. Okay, quick details about all these basic components we've just talked about. Panels. This in previous projects, this has always been a major debate because somehow this was very important for the stakeholders. Almost all of the solar panels you can find are manufactured in China today. Sometimes you find made in Germany printed on them, especially I see that a lot of times in Africa. I can tell you it's fake. We have hardly any solar industry left. They all come from China, and the difference in quality is yeah, mainly superficial. I mean, usually what you can buy is fine. So this is usually a no-brainer. The bigger difference is more in the flexibility and the rigidity of the modules. So you can get flexible ones. You might know them from applications on yachts or for camping, and they are much lighter, but they have a limited lifetime. And they get advertised as being flexible, that you can bend them to round shapes. It's possible, but it's actually damaging them. So the main advantage is here they are lighter. And then on the other hand, you have the rigid glass modules with aluminum frame for house installation or for domestic use. They're usually rated up to 20 years of lifetime with guaranteed power output. Usually they are locally available around the Pacific region, probably at a high price. So your choice here mainly depends on what is available, what is the price, what is the weight. In particular, when you put them on a boat, weight is always a concern because on the top, you don't want your boat to tip over. And then what counts is the voltage at the output, because the voltage has to fit to these solar chargers. So these MPBTs I've mentioned before. MPBT actually stands for maximum power point tracker. What these guys are doing is they regulating the output current and voltage of the solar panels, because power is the product of voltage and current. So amps times voltage is watts. And you want to maximize your power output, your watt output. So you need to find the maximum power point. And this is what these guys are doing. It's basically small microcontrollers adjusting that all the time according to the environmental conditions, and then feeding it into the batteries. They are a little bit more expensive than other technologies. For example, PWM solar chargers. PWM can also be used on smaller systems, but they are far less efficient. And actually, I'm not aware that they are available on the very big scale. So when you go beyond a very small panel for a solar light or something like that, you're gonna end up with MPPTs anyway. And they boost the performance of your system quite a lot. It's important that these MPPTs fit to the panels or the other way around, and of course also to the batteries, voltage-wise and amp-wise, that your system is designed properly. What I mean with that is usually these MPPTs have an input voltage, and you don't want to, of course, put too much voltage in because then they're going to be damaged. So you have to take care that the strings of your panels do not overload your charge controllers. Next basic component are the batteries. Recommendation for the type of vessel we're talking about here are lithium iron phosphate or LiFePO. That's a type of technology that is different from what you see in most electric cars. Different in the way that it's a little bit more heavy than these lithium batteries in the cars, but on the other hand, they are way more safe. They can't explode, they cannot catch fire, and they're also a bit more affordable. So these batteries actually look like regular car batteries. I mean, lead acid batteries from a combustion car. And for application, you can either use one of them, or you can stack up multiple ones to a so-called battery bank, as you see on the right-hand side, either in series or parallel, to also match your system voltage. So in this example, on the right, you see on the left side, 48 volt battery bank with 100 amp hours, which consists of 4 12-volt batteries. So 4 times 12 is 48. That's how this 48 comes around. And they are just connected with jumper cables. And this would be a typical installation of this type. Costs you can expect here are around $250 per kilowatt hour. Shouldn't be much more expensive than that. But as you can see, this is a price driver. If you have 20 kilowatt hours installed in your vessel, then we're already talking about $5,000 here as investment cost just for the energy storage. So you always want to keep your battery size small. Next part, the engines. There you basically have two options today, which are outboard engines and inboard engines. Outboard engines, I guess that's commonly known. It's just what you put on the back of your boat. You can buy just the product and put it on and use it. There are a couple of manufacturers. Oh, by the way, if I show certain photos here with company names or brands on, that's just for reference. It's not a recommendation in any way. So this is just I'm just showing different photos here from different brands. Try to balance that a little bit so I don't make any recommendation here in no way. So you mainly have 2 to 3 large manufacturers of these electric outboard engines. There are a lot more smaller ones. Generally, they are easy to install, easy to handle on a light craft. But the big problem with these engines is many times they are made for leisure use. They are not made for commercial use. To give you an example, these engines we're using on a ferry in Uganda, they are rated, or they have a service interval for their internal shaft gaskets of 700 hours. And I was talking to the manufacturer and asking why it's just 700 hours, and they were really surprised that 700 hours that last forever. But when you think about it, you use the ferry 2 hours a day, then you have to change the main gasket once a year. And if you use it 4 hours a day, then yeah, it gets even higher, but this theory will be used 8 hours a day. So we are constantly keep on changing. Every couple of weeks, we are changing the gaskets now. So it's really not made for commercial use. That's what you have to keep in mind. I'm not aware of any outboard engine right now on the market that's fit for commercial use. If you find one, please let me know. Second option would be inboard engines. Basically, you have the engine inside of your hull, then there's a hole in the hull where the shaft goes through and the propeller sticks out. It's way more difficult to install because you need engine mount inside of the hull. You need to have a hole in the hull. You somehow need to make that waterproof, so on. Also requires separate steering gear because the engine cannot be turned like is the case for the outboard engine. And it can also not be retracted in case you don't want to have your propulsion equipment sticking out of the hull. So it's always a trade-off. But at least you can find these engines for commercial use. And they're also more durable for commercial use. Shore connection for charging from public grid if the solar is not enough. This has always been a topic coming up quite frequently, and I've seen projects starting to talk about setting up charging stations similar to those that you see for cars. So with the car chargers and very expensive equipment. From my point of view, that is not necessary at all. This type of caravan charger, I mean, in Europe, we call it caravan plug. It's pretty common around yachts and small boats for their hotel load when they're in the harbor. This is completely adequate when you have 16 amp or 32 amp, depending on what your public grid can deliver. One of these plugs, last time I checked, cost $3, and the cable is not much more. So we're talking about a very, very different price range here when you want to set up charging stations. And I think that's really important. If you come with a charging station where the plug alone is about $300, nobody is willing to invest in this type of technology. One important side note here is when you consider shore charging, so not only relying on solar, you have to keep galvanic corrosion in mind. Just want to mention that here, I will not go into the depth of it, but this is definitely a topic you have to be aware of, especially if your hull is from aluminium or steel, or you have an inboard engine where the engine is always in the water. If you don't take care, this can destroy your vessel in no time. So you have to be really careful about this. Yeah, and last but not least, the hull or the platform for your vessel. There are a few things to consider here. First of all, it's stability. And stability in ship design means will it tip over or will it stay afloat upright? And when you look at, for example, these photos on the top here, on a monohull, so a ship with one hull, it's and you put something very heavy on top, it's kind of obvious that it might be at risk of tipping over. So this has to be taken account for in the design process, or when a retrofit is done, has to be evaluated very carefully. So there are no accidents or no difficult situation, dangerous situations arising from that. What we often use for that reason are catamaran designs with two hulls, where we also have way more deck space for cargo, for people, but also for the canopy, for the solar panels. So we have more area and just more power in our system. And at the same time, we also have a more stable platform. So my point of view, these catamarans are really, really well suited for this type of propulsion technology. Although I have to mention, when you operate in small canals or on rivers, or when you have port infrastructure that doesn't allow for a wide vessel to dock, then it might not be the ideal solution. And that's actually why you see on the top photo That's from Cara Solar. That's a project from the Amazon River. They have narrow rivers and waterways and channels where they have to navigate. So they opted for this monohull design. But that makes essentially, that's limiting your superstructure, your canopy for the solar panels. So you have to be very careful what you put on top there. Hull shape. I already mentioned you have to be conservative with your energy, and that also translates to the drag of the hull. So what you want to see here are very slender, low drag hulls that are fit for the design condition of the boat. So in other words, for the speed that you want to travel at. When you just take a conventional motorboat from the shelf, this is going to be optimized for planning speed. So for, let's say, at least 10 knots. But you're never going to sail 10 knots with your solar boat because it's way too fast. It's way too much energy you're blowing out there. So you really want to take care that you have a hull that is fit for slow steaming, but also for low drag by being slender and just streamlined for this purpose. And of course, the whole thing needs to fit for the environment. When it comes to draft, when you want to pull it up a beach, you need some rocker on the front end. So the front end must be bended up so you're not ram it into the sand and get stuck. When you're operating in a coral reef environment or you fall dry frequently, you might want to think about keel protection so you don't scratch your hulls all the time and get holes. And also an important role is the style of docking that's preferred by the later operators. So that's, especially when it's a passenger boat, where do people enter? Where do people leave? What kind of accommodation do you need? So all these style of things influence the design as well. That's about the technological part. Now the challenges for sustainable implementation that we have encountered in previous projects, in particular in the Pacific region, but I'm also influenced a little bit by the projects in Africa, where we have different, partly more extreme challenges, but I think there's also a lot to learn for the Pacific region. First of all, it's a supply chain and procurement. There are no, at least to my knowledge, there are no off-the-shelf products available. We've seen that in the beginning of the Samoa project, where the project tried to just go ahead and use the budget to procure solar electric boats. And then I figured out, oh, they're not available. There's nobody around making them. There is no big manufacturer like when you want to buy a car, you go to a car dealer and buy a car. But there is no such thing for these type of boats. So you have to be aware of that, and you also have to be aware of the almost non-existent supply chain throughout the Pacific region, in particular when you come to the islands. At the same time, almost all of the equipment, all of the stuff is produced in Asia, mainly in China. So it's already there. It's just poorly distributed throughout the region. But you can find everything you need for this type of vessel in
Second, there is no one-size-fits-all solution available. These vessels, as I mentioned, you cannot really buy them off the shelf in the first hand, but also you really have to take care of designing them properly for what you want to do with them. And this is also closely related because you're limited in your energy storage and production. And so you really want to have a vessel that works for the intended use case. like displacement, speed, distance, charging options, solar power, the budget you have, etc., etc. Also, what you have to keep in mind is recycling at end of life. So, for example, on the Pacific Islands, they have no waste management or no recycling management for electric components implemented yet. So everything you dump there gonna stay there somewhere on the reef in the environment. That's also something always concerned about. And last but not least, knowledge of the user and technician is, at least in the Marshall Islands, as of now, non-existent because there are no electric engines, no electric boats except the one that was implemented by the GIZ project. So there are also no people who can repair it or use it properly. So what we really need there is training and capacity building, and that's what we're going to do in the next project step starting this year. We're going to team up with CMI, College of the Marshall Islands, to implement this type of knowledge into the public curriculum. So it's going to be sustainably implemented in public education for the coming years. All right, let's have a look into exemplary business case. As Rafael already mentioned, this ferry service in the Majuro Lagoon. There is this small island called Anico where they have a regular ferrying service too. Distance is about 6 nautical miles or 11 kilometers. Protected lagoon, well, relatively protected lagoon. We have a high sun radiation because it's close to the equator. Usually the boats do up to 3 round trips a day. I estimated they do that 300 days a year, might be a little bit less, might be a little bit more. And they can carry up to 20 passengers a trip, but they usually don't do. They carry much less.
Henrik, sorry, just to mention, we have a bit more than 50 minutes left before the end of the session. We can perhaps go a bit over time if you're available, but just wanted to mention.
Okay, all right. I'm gonna speed up a little bit. Yeah, looking at the capex cost of these vessels, we see they are pretty equal. Although the one boat has a battery, the other one has not. But yeah, their electric boat is a little bit more expensive, but it's not that much. This is all based on the cost of battery for $200 per kilowatt hours. Looking at the operation cost, we see that the gasoline that the petrol boat today consumes amounts to about $23,000 a year, while the electric boat just has an operation cost of about $2,400 a year. That includes overnight charging every night. And during the day, solar power is counted in for. Maintenance and upkeep is roughly the same. So in the end, over a period of 15 years, the costs for the petrol boat amount to $365,000, while the solar electric boat is just at $60,000. This already includes a battery swap after 7.5 years or 3,000 cycles at 60% depth of discharge, but does not account for that the old battery could be sold or used for other applications at their reduced capacity because it's not broken. So there's a huge benefit already on the cost side for just investment and operation of a solar electric vessel compared to a petrol boat. And what does it mean? We have roughly $20,000 saving per year in this scenario. And these $20,000 stay in the country. They are not blown out to buy petrol and finance someone's skyscraper. So this is just money that stays in the country and can be invested locally for communal benefit or for expanding the business. So there's just a really large potential that I see, yeah, in this technology. Quick guideline for implementation of these projects. First of all, information about the technology is virtually unknown to many public and private stakeholders today. So there is a lot of work needed, basically like this workshop that we're doing right now. So spreading the knowledge about the opportunities, that's very important. Also, training is needed. Technicians, operators, administrators, you need to train all these guys. There's virtually nobody available who can fill this roles on the spot. Then you're gonna need to provide some financial solutions because there is, as we've seen, there is a little bit of higher investment and also risk associated for first movers. And that makes it sometimes, less attractive compared to the solution that is already known. And for this public-private partnerships or international cooperation, like, for example, the GIZ project that Raphael presented can really help to accelerate implementation of these technologies. And also more training, more capacity building is needed. Training a second time because it's really important. And this should be done in a sustainable way, for example, by implementing the knowledge into the public education system, as I've been mentioned before. Really see a key component there that this knowledge is not somewhere in a book collecting dust on a shelf, but it's really, in the public education, and that a broad spectrum of people can access it. I mentioned all of this already, so I'm quickly jumping over it because of time constraint, but you get the presentation anyway and can have a detailed look at this. Time for question and answer.
Perfect. Thank you so much, Henrik. So you can share your questions in the chat. We did have one question from Moshi in the chat regarding the kind of the value chains and supply chain issues and how much the value chains relate to rely on the Chinese supply chain. Raphael did answer that. He did mention in the chat, so he did mention that that many of the boats are used. The lagoon boats, the WAM, is that the Uganda ones are built with hardware store components only, and you would know a bit more about that. So maybe you can say a few words. And then there's another question on the corrosion issues due to salt water that you may want to touch upon quickly before moving over to Jonas. Thank you.
Sure. Yes. What Raphael means, the WAM boats, that's the one that were built in the Marshall Islands, the small yellow canoes. They only use hardware store equipment like plywood, fiberglass for the hardware, but they are not really equipped with electrical propulsion yet. So for these, as I mentioned, for the basic components, engine, battery, charge controller, solar panels, all this stuff comes from China. Wherever you buy it, if you buy it in Europe, America, somewhere else, it all is imported from China because they just have, they're the market leaders for some reasons I don't want to elaborate on now, but they are today controlling the market. And there's just no way around that. I mean, you will have a very hard time looking for components that are manufactured somewhere outside of China. You might find some in Taiwan, you might find some in Southeast Asia, but you will generally have a hard time. But the main point I wanted to make there is, since we are here talking about the Pacific Asia region, you have all the equipment there. Actually, you have a better supply than we have in Europe because we have to ship all that stuff first. But it's just unevenly distributed. On the islands, you find nothing. In developing countries, you also find hardly anything. And in China, you have all the factories that make it. So there's a bit of a distribution problem here. But basically, you have everything in the region that you need. And what was the
Great.
second thing
And
about
the second was on the corrosion due to salt water.
corrosion? Right. Due to salt water. Are there any more? Let me quick have a look in the chat if there are some more
There is one
detailed
more question on performance monitoring framework for pilot vessels. I'm not sure if that's something Jonas could also respond, but
Andrew Jeffries asked that corrosion issue to salt water.
yeah.
I'm not sure what kind of component he's concerned about, but yeah, you have to take care that whenever you operate in a marine environment, you limit your weak spots for corrosion. So you want to limit, for example, unequal materials like aluminum and stainless steel, so that you isolate them from each other. You want to use materials that are corrosion proof for the environment you're operating in. And when it comes to the electric system, you want to make sure it's not exposed to the elements, so that it's protected in some way. That's very important. And as I mentioned, there is this galvanic corrosion. That's always a risk when you're using shore power supply. Don't want to go into the depth. We don't have time. But what you need to do is you need a galvanic isolation there. And there's the easiest way is that you buy an isolation transformer that's providing these galvanic isolation. If you, yeah, just Google galvanic isolation transformer or yeah, in general galvanic isolation on electric boats, you will find diagrams and in-depth explanation. There's the knowledge is out there. Just need the keywords to look for it.
Super, thank you. And there is one more question. I'm not sure if this one will be responded by Jonas in his presentation, but speaking about performance monitoring framework, if you can speak about a performance monitoring framework for pilot vessels.
Not quite sure what that means. Well, performance monitoring, it always depends if you want to do that over a long time or if you just want to make a sea trial and see, okay, it can go as fast as we calculated, it can go as far as we calculated, so it's fine. Or if you want to, yeah, collect data from a long time, let's say a year or longer in operation. So there are completely different challenges. Making sea trial, recording speed, recording energy consumption, that's no problem. I mean, you can do that on the vessel. You don't need any fancy equipment. You just make a sea trial, and then you have your data. If you want to monitor over a long time, then you need some sort of measurement equipment on board that's feeding the data either into a local storage, then someone would have come and pick the local storage every once in a while, which is a bit inconvenient in remote locations. Or you would need to set up a system that's uploading the data online, which is also not always possible because you need data connection. If you have no LTE or that sort of coverage, then you need some satellite connection, then it's going to be very pricey. Another option would be that you could use AIS if you equip your vessels with radio that is AIS capable. It can automatically send out this data to commercial providers, where you then can, for a access fee, access your data, but the information is limited there. So it really depends on what you need here. If you need the full set of operational data, or if you just want to know where it's going right now, or yeah, if you just want to make one sea trial and see this is what we now have and now use it.
Okay, thank you. We have one more question from Amelia, but I think in the interest of time, I suggest we take it at the end. Let's hand over to Jonas at this stage. And if you are available to stay a bit over time, we can then take the question after Jonas's presentation. So over to you, Jonas.
Yeah, I hope you can see my screen and the slides.
Yes. Yes, and
So
your cursor is also available.
yeah, thank you for the introduction, Johanna, and thank you for your part, Raphael and Henrik. So yeah, I will try to speed up my presentation a little bit. Nevertheless, I calculated it for 20 minutes, so I won't be able to skip every slide. Yeah, I would like to introduce to you the case study for the green water taxi. And this is a R&D project which was established in 2016. And it is a project that is funded by the European Union and the Interreg project. And this project is developed to transport cargo and passengers across the German Wadden Sea. And the first, we were part of the Mary Green project from 2016 to 2018, where we developed the prototype for the water taxi. You have to keep in mind that when you apply for a project, you start at least 1 year before the project start to apply for funding. So that was in 2015. That is 10 years ago. And what that means for the project, I will explain later on. We took part in another project, the H2Watt project, in which we developed a methanol range extender from 2018 to 2020. And since 2020, we are operating the green water taxi for teaching purposes at our maritime campus in Leer. For some reason, I have this. All right, now it works. Sorry, I thought I had the same problem as Raphael, but now I can skip the slides. Just to give you a quick overview of the scenario, the Wadden Sea in Germany is a sensitive area, and it's part of the National Park Lower Saxony Wadden Sea. It has a unique geology. That means that large regions of the sea fall dry on low tide, and the bottom of this sea mainly consists of mud, gravel, and sand. It looks somehow at low tide, it looks like a brown desert. In the picture on the right side, you can get an idea of what the sea looks like here. Nevertheless, if you are used to sand beaches and blue water, then somehow it might look not that nice to you. Nevertheless, it's a very important habitat for many plant and animal species. It has a very huge biodiversity, and the whole region is a very important stopover for migratory birds and a vital habitat for fish, crustaceans, and other marine species. Just to give you a quick overview, you can see the map here, and the bright blue colored regions, all this is what? So these, in between the mainland and the islands, these regions are falling dry on a low tide, and you can see that there is barely more than water between mainland and the islands. Nevertheless, because of this, the shipping, or for shipping companies, these are special challenges. Some of the harbors of the islands are only reachable at high tide. This depends on the position of the harbors. If these harbors are positioned on the sides of the island, then they are closer to the outlets. In between the islands, there are stronger currents and there is deeper water. If the harbors are positioned in the center of the island, there you have less current and you have more shallow water. All the goods and personnel is mainly transported by ships to the islands, and tourism is the main economic sector on these islands. Well, the case that I would like to present to you is the passenger transport to the island of Juist. Let me just quickly jump back. The island of Juist is this one. And as you can see here, we have the harbor in the center of the island, and you can see the shipping route here. There is a large ferry that transports personal and goods to the island, and this is the blue route that you can see. This ferry has a draft of approximately 1.2 to 1.4 meters, and the round trip for the large ferry is 20 to 24 nautical miles. It's operating at 7 to 10 knots. Nevertheless, there is another route, this is the red one, which smaller boats can take if they have less draft. And this is where water taxis come into the, this is the route that water taxis can take. Due to their reduced draft, they can take the direct route, which is approximately like 50 nautical miles for a round trip. This is the large ferry, or this is a picture of the large ferry. There's different ferries between the island and the mainland, or each island has its own ferry. So somehow they are all similar. They have a very flat bottom, but they can be compared. The large ferry can transport up to 750 persons, and the duration for the trip to the island of Juist takes 75 minutes. Ticket prices are 22 euros, and in comparison to the water taxis, you have less CO2 emissions per passenger compared to the water taxis. What are the water taxis? You can see them here. So these are small, fast boats. They can transport up to 10 persons plus 2 crew members. Duration per trip is 45 minutes, and ticket prices are up to 52 euros. CO2 emissions are higher than compared to the passenger ferry. Somehow this stands in strong contradiction to what this whole area stands for. Like, we have a strong biodiversity. Nevertheless, somehow this fast transport emerged due to the fact that there's only one ferry to the island, and people are willing to pay more to get faster and oftener to more often to the island. And this is where our project, this is what our project was developed from. We made a prototype, or we constructed a prototype for a sustainable sea transport to the island of Juist, and tried to replace these water taxis, which are powered by internal combustion engines, with a platform that is powered by two times 50 kilowatt electro outboard engines. We have a battery capacity of 2 times 38 kilowatt hours lithium ion NMC battery, and we have a very small solar roof. If you keep Henrik's presentation in mind, then we have here really a very small solar roof in comparison to the installed electrical power. The draft is 0.2 meters, which was a requirement, and we have a service speed of 15 knots, which is somehow something that the water taxis are actually navigating with. When it comes to energy consumption, and perhaps this is also something that the question that came from the chat was addressing, of course we are able to monitor the energy consumption, but you can see here on the right chart that the range with the installed battery capacity is really decreasing if the speed is increasing. For the required speed of 60 knots, we have approximately 15 nautical miles range. There is a sweet spot somewhere here at 11 knots, where you can see that the range is something like 22 nautical miles. But nevertheless, we need to address that. Energy consumption at high speed is an issue when it comes to implementation in the given scenario. So optimization to an operating point is necessary. And I would say that the operating point for this shouldn't be like 16 knots, like the water taxis that are running with the internal combustion engines. But I would suggest to go slower in this case. The reachable operation range always has to be calculated with a buffer, and boat operators have to keep in mind that the state of charge of the batteries, and thus the remaining energy, is sometimes not linear, depending on the cell technology of the battery management system. That means that if you are going below 20% state of charge, you will recognize that the state of charge is decreasing faster than in comparison to the state of charge between 20 and 100%. So you could say, why don't we just double the battery capacity in order to double the range? It's not that easy. We have made different measures or measuring runs, and of course, additional weight will significantly reduce the range as well. The requirement is to transport persons and cargo, and if you add like 500 kilograms extra for additional batteries, this will result in other, you will end up in other problems. You will need stronger hulls, a stronger superstructure, which will again increase the weight of the whole construction. So thus doubling the battery capacity does not double the range. There's other things which needs to be recommended. External influences like waves, wind, or strong currents may further reduce the range. And one other thing that we discovered during our measuring runs is that also fouling on the hulls during the season may reduce the efficiency by 20%. So you really have to keep an eye on the installed battery capacity, or you really need to calculate that with reserve. As you can see here on the chart on the right side, a good operating point here when it comes to speed is 11 knots. Going much faster, like the required 16 knots, you can see that we are doubling here the output power, but we are not doubling the speed. This is something that Henrik already mentioned. What are we doing, or what we actually are doing here at the University of Applied Sciences Emden Leer is that we introduced a curriculum for energy efficiency in ship operation, and the students get in touch with these new propulsion technologies. These are students that will become that work in the nautic industry later on, and they have the possibility to get to know these new propulsion systems, and we are raising the awareness for the challenges in sustainable sea transport. We are executing measuring runs to determine dependencies. And the great thing about these electrical engines is that they give really a direct feedback to changes regarding trim, regarding additional loads, or even external influences like winds and waves, or the increased resistance by fouling. All this is monitored with a data logger, but nevertheless, the students are also asked to make own notes. This is part of the curriculum. They record the data by hand. They read the data from the display, and they need to protocol them. For them, this is really ship operation under limited energy availability. and they can see what nautical decisions, how nautical decisions may affect the remaining range. That means like that going at full throttle will really drain your batteries, and if you are low on battery, you really need to slow down and try to find your way back to the harbor at the site of the in shallow waters where the current is less strong if you are going against the current. When it comes to capacity building, I have to emphasize that electric marine propulsion systems require special knowledge in maintenance. Although you can often hear that they are low at maintenance, you need special knowledge transfer. That means that basic electricity or electrical engineering and sensor technology is crucial to perform diagnostics and fault detection. And there is another aspect which I need to mention. All the systems are delivered with service documents. Knowing and understanding these documents is mandatory for the boat operators. We are actually the upgrowing generation is used to videos. Videos which are presented in a very short format, but understanding and reading documents is something that we also implemented in our curriculum. You see that on the right side, this is the system architecture of such a electric propulsion system, and they are connected with cables. There is the high voltage system, which we are not able to touch, but nevertheless, all these systems are connected with cables, and sensors run from one system to another. And in order to perform diagnostics and fault detection, it is good to have a basic knowledge in electricity and electrical engineering. This is something that we are implementing here in our curriculum, and this is also something that is important to implement into the public into the curriculum at public schools in remote regions in order to understand the technology. If we would implement this project again, then I would say charge rate is the game changer. The battery technology of the green water taxi is already rather old. It is from 2013, and the typical charge rate for this project is 0.25 C. The charge rate is the measure of charge and discharge rates relatively to the battery's capacity. A higher charge rate allows faster charging. So that means for our battery, which is approximately 80 kilowatts, we can charge with a maximum at 80 kilowatt hours, we can charge with a maximum of 20 kilowatts. So it takes us 4 hours to charge from 0 to 100%. And if you keep in mind that you don't want to go lower, that you don't want to go below 20% because you want to keep reserve, it takes you at least 3 hours to fully charge the battery. I have a chart here on the right side with the comparison of the latest cell technologies. When it comes to the cathode chemistry on cell level, this is what actually influences the characteristic of the batteries. And you can see that here the latest generation of the LFP accumulators that Henrik mentioned already allowed charge ranges between 2.5 and 3.5. If you take into account the cutting edge technology, which is here on the left, there is also C rates from 4 to 5, which are possible. Nevertheless, if you take a look at the performance and the qualitative cycle stability safety here, then you can see that perhaps for maritime technology, this is not the best choice. There is one more thing which needs to be mentioned. The marinization of cell technology takes its time. In comparison to the automotive industry, this is a niche technology. So that means that it will take time till the latest cell technology will be implemented for maritime technology. What have we learned from this project? We have learned that the higher charge rates would allow us recharging while passengers are boarding and deboarding. The latest cell technologies would allow charge rates up to 3C, so that means that we can charge from 20 to 80% in 15 minutes. Nevertheless, this also implies difficulties. High charging rates require additional infrastructure at the dock. If you calculate 3C for our 80 kilowatt hours accumulator or battery, that means that we are charging with 240 kilowatts. So such a maritime e-mobility concept can be divided into different subsystems. You have the hull and the propulsion system. You have batteries and a battery management system, plus eventually an onboard charging system, and you need the dock and the charging infrastructure, plus the electrical supply line. This is one point which I really want to emphasize. In remote regions, such a electrical supply line for charging with high currents may be really challenging. Even here on the German shoreline, these charging electrical supply lines are implementing difficulties because you need to get the energy there, and we are talking here about currents that can't be delivered by a normal 220 volt plug. What else have we learned? The project amortization for pilot projects may not always be the primary target. Nevertheless, funding may help to build up a local capacity. And what was the result of the project for the green water taxi? The shipping company, the Frisia, that also took part in the project, they recognized or they realized that scaling effects, also the cost of the crew must be considered. That means that if you have less crew and you have more passengers, the return of invest or amortization may be better. In the end, they introduced the Frisia E1 this year, which is a fully electric catamaran, which can carry up to 150 persons. It doesn't navigate to the island of Juist, but the island of Norderney, which is the one which is to the right of the island of Juist. However, this is something, this is a very important point. High voltage battery technology now and then requires OEM support. So this is not something that I would suggest for remote Pacific regions. It is better to stick to the 48 volt technology that Henrik already mentioned. And the cutting edge battery technology is introduced in the automotive industry. Certification, if required for maritime application, takes its time. Certification certification is a thing that may become which may be required if you are running, if you are developing ships that can carry more passengers. Nevertheless, investments in renewable energies such as photovoltaic and wind power may also boost the amortization of e-boats because you have energy available at a relatively low price. Just to give you a short comparison, in Germany, we currently pay 30 cents per kilowatt hours if we take it from the net. If you install a photovoltaic, or if you install PV panels and a transformer, you may harvest sun energy for 7 cents per kilowatt hours and charge that into your electric vessel or into your car. For implementation in remote regions, I would rather take solid technology than latest cutting edge technology. And yeah, to come back to what Bart said in the intro for this session, the Yamaha Enduro engine for maritime e-mobility still needs to be developed. I guess on the rivers of Bangkok, there is for sure some of the Yamaha Enduro two-stroke engines which somehow emit the smoke that you can see there on the water. But this engine was developed like 40 years ago and is still sold in the Pacific region. What we really need is a Yamaha Enduro engine for e-mobility on the water, and this still needs to be developed. If we have this, then we have yeah, we are really it will become much more easy to implement these projects. Okay, so if there's any questions right now, then don't hesitate to ask.
Yes, any questions for Jonas at this stage? We are running a bit over time, so apologies for that. But I think the session has been really informative, and I see quite a few people have stayed over, so I hope it has still been helpful in terms of kind of providing all the information that our trainers had planned for this, running a bit over time. So there we have one question. So have there been any innovative ways to address the challenges of infrastructure and geographical access for charging stations? Oh, this is in the Pacific. I saw Amelia also had other questions
I'm typing
on the
right now.
Pacific
I can also
context.
answer. I can also answer directly to Amelia. I'm typing a reply right now.
Okay, that's
Actually, I
great.
have 3 questions. Yeah, if you're okay, I would just answer it verbally.
Sure.
No,
Very
no, she's
briefly, if
still
you
there.
can, then that's great.
Okay, first of all, did we encounter people's perceptions on solar tech as a challenge? Generally, no, because, well, all the projects I've been involved with were set up in a way that the people said, "Hey, we wanna try this," and not the other way around. So it's always usually coming from the partner side. So there were no challenges. In Uganda, I have to say, people constantly, like people who are not involved in the project, constantly ask us still if the engines are 2-stroke or 4-stroke. So there's really a lot of training and information needed for people to fully understand the potential. And I think many people still wait for the time when we have to buy gasoline. And they didn't realize yet that these engines don't need gasoline. So there is a lot of training necessary, because yeah, depending on where you work, this knowledge might not be there. Batteries, yeah, later use of batteries. It's common practice that automotive batteries are used as stationary buffers for solar applications, for example. So when they are beyond their, let's say, lifetime, it's not really their lifetime, but when they are not suitable for the application in the car or in other mobility, because their capacity dropped. I mean, everybody knows that from a phone. When you use it for a few years, the capacity of the battery really drops, but it's still working. So it can still be used in a configuration where weight is not a problem, where you can just store a lot of like secondhand batteries and use them for stationary capacity to store, for example, excess solar power or wind power. And this is commonly done. This is already implemented in many places. So it could be used for these kind of applications. If you're reading the third question, capacity building across multiple stakeholders, what ways are your project looking to integrate into structured formal training, if at all? So maybe I give you the example for the Marshall Islands project that we are now expanding. There we'll work with the College of the Marshall Islands as a public national college to implement basic curricula for this type of technology. So marine application for solar electric propulsion, something like that will be the title. And it will cover pretty much everything that we've been talking about the past almost 2 hours, but of course, in a far greater detail. And the goal is that the students who participate in the end will be able to operate and maintain, and some even may able to design these kind of vessels. So that's pretty much the goal. And it's also implemented in the public education system, so it's gonna stay there. And everybody can access the knowledge. I hope that answers the question, and I hope that you're still there.
I see Amelia is still there, so thank you.
Great.
Thank you, Henrik, for this responsive. I think since we have now almost run 30 minutes over time, and I don't see further questions, I think we will be wrapping up. So
there's one more about charging stations, also from Amelia.
oh, okay, yes,
Yeah,
true.
quickly answer that one. Charging stations, I don't see a big problem with the charging stations, actually. That's why we're talking about solar electric vessels, because then you are less dependent on the charging stations. And usually I always get this sort of feedback from project implementers that they look a lot at the charging stations, because they know that from the automotive sector, that you always need a lot of charging stations. But this is not so much the case for electric propulsion. These charging stations are, I mean, it depends a lot on your project setup and your vessel design and your, basically what you want to do. It always depends, but generally speaking, this is of less importance for this sort of application. It's not a showstopper if you struggle to find charging stations, or if you have an unstable public grid. It's not so important as you might think.
Perfect. Sorry, I missed out on that question. I think now there should be no further questions. I see no hands up either. Yes, there was Amelia is thanking for the responses. So I would like to extend a very big thank you to Rafael, to Jonas, to Hendrik for this really informative session. We ran a bit over time, but I hope also our participants enjoyed. The recording will be available. We will be sharing it per email next week together with the PowerPoint slides, so you can have a look at the detailed information that was presented. And yes, so thank you all of you participants as well for your active participation today. It was great to see all these questions coming in as well. And yes, thanks again, Rafael, Jonas, and Hendrik for all your inputs today. And yes, we'll look forward to seeing you in our future events as well. Thank you so much.